Hi friends, in this class we will be discussing the two-phase simplex method, the second method of solving a LPP, linear programming problem. And what we have done in our previous class is we have solved a linear programming problem using simplex method. So why we have introduced the two-phase simplex method is some disadvantages uh, or yes, some disadvantages is associated with our previous method, that is simplex method. So that is why we go for the two phase of this simplex method, phase one and phase two, that is two-phase simplex method. And in two-phase simplex method, as its name indicates, we got two phases, phase one and phase two phases. And okay, so what we will reach into a simplex method from simplex method by addressing the disadvantages or yes disadvantages of or the drawback of this simplex method, and then we will address that, and then we will go for the two-phase simplex method. Okay, and in simplex method we have that problem like this. We have the problem, for example, we have a minus x1 minus x1 minus 2x2 minus x3. This is our f. So minimize f. This is our objective function, our problem. Subject to the constraints are 2x1 is 2x1 plus x2 minus x3 less than or equal to 2, and minus 2x1 plus x2 minus 5x3 greater than or equal to minus x, like this. And 4x1 plus x2 plus x3 less than or equal to 6. So what we have done in our simplex method is we have first we have we have converted this into our standard form, right, by making the constant terms all positives or either positives or zeros. That means this minus 6 we have multiplied with the minus 1, right? So in two-phase simplex method, the first step you have to do is this also. This also the first step you have to do. That is conversion of the given problem in standard form. Okay, standard form of a LPP. So first you have to do that, and that means after the conversion into the standard form, we will get a set of equations, and that set of equations is known as system of linear equation. Okay, that's up to that we have done in simplex method. So recall that procedure. Okay, and uh, then also we have introduced slack variables and surplus variables, right? So that also you recall. Okay, that points also you should remember. And what we have done is that we have introduced x4, x5 and x6 as slack variables, and these slack variables are taken as the basic variables. in our tabular columns, in our tables, in our iterations, right? So these are known as the basic variables, and non-basic variables means x1, x2, x3 are the non-basic variables. And what we have done is, in that situation we got a solution known as basic feasible solution. Okay, basic feasible solution we got at that time in simplex method, in applying the simplex method. So how we found the basic feasible solution is, we equate the non-basic variables equal to 0, and we got some either positive or 0 solution for the basic variables x4, x4, x5 and x6. Like x4 equal to, we got 2, and x5 we got it as 6, and x6 equal to 6 we got, like this. So this solution is known as our basic feasible solution, right? Basic feasible solution. So before that we understood that the yes, we got the basic feasible solution. Why? Because we got an identity matrix there, identity matrix 1 0 0 0 1 0 0 0 1, like that. We got an identity matrix in the case of slack variables. In the case of basic in the by inspecting the basic variables x4, x5, x6 and minus f, then we examine that forms a identity matrix, right? Then we put the non-basic variables equal to 0, and we got the basic feasible solution in that case, right? Suppose we we didn't have this identity matrix formulation. We didn't have that identity matrix formulation. Some we got here some 1, we got 1 1 0 we got, or 2 2 0, or 0 2 0, like that. Another non-identity matrix we got, and at that case, suppose we got like that, then what we will do? So the answer is our two-phase simplex method. So you have to go for the you go for the two-phase simplex method. That means the thing is, you have to go for this two-phase simplex method whenever an initial feasible canonical form may not be readily available. Okay, that means this is the case when the LPP does not have slack variables for some of the equations. For some of the equations, they don't have slack variables, or when the slack variables have negative coefficients also. Some of the slack variables have, or some or all of the slack variables have some negative coefficients. In that case also, this matrix, identity matrix formulation will not happen. So in that case, we will not get the basic feasible solution, right? Basic feasible solution is impossible. So in that case, we will go for the two-phase simplex method. Okay, and another drawback of this simplex method is, while solving a LPP using simplex method, sometimes we may not get all the minus f row all positives, or either positives or 0. That condition we will not get, right? In that case also, we will go for the two-phase simplex method. Okay, so this is our introduction, and so this is why we will opt this two-phase simplex method. Okay, Okay, we will consider a problem, and we will explain how to solve that problem with two-phase simplex method, so that the algorithm also will be clear, uh, and you have to just go through the algorithm once. You will be clear, very clear. Okay, so the question is, solve the LPP using two-phase simplex method. And problem is, minimize the linear function f is equal to 2x1 plus 3x2 plus 2x3 minus x4 plus x5, subject to the constraints 3x1 minus x2, sorry, 3x1 minus 3x2 plus 4x3 plus 2x4 minus x5 equal to 0. And the second linear constraint is x1 plus x2, x1 plus x2 plus x3 plus 3x4 plus x5 equal to 2, and xi also, xi greater than or equal to 0, I varies from 1, 2, 3, 4 and 5. Okay, so this is our problem. So before this, if you observe this problem, you will observe that all these constraints are containing equal to expression, equal to. So these are equations, not linear inequalities, like less than or equal to, greater than or equal to, like that, right? If the examiner has given linear inequality equations like this, okay, this is some, for example, this is some 3x1 minus 3x2 plus 2x4 x4, okay, 2x4 greater than or equal to some 0 or something like that. Then what you have to do, you have to introduce, like what you have done in our simplex method. You have to introduce here it is greater than or equal to, so you have to make it an equation. So you have to introduce a surplus variable. You have to subtract a uh, surplus variable from to this inequality, this, so that will become 3x1 minus 3x2 plus 2x4, right? 2x4 minus x5 equal to 0. So actually this minus x5 is nothing but your surplus variable. Okay, up to that, maybe it can be or cannot be, because this x5 is this x5, which is a variable, this is present in our minimization objective function also. This objective function also, this is present, x5 variable. So you cannot say, because this actually in our previous method, the simplex method, we this surplus variable that is only introduced in constraints only. Okay, so you cannot say, but this is the procedure. This is the procedure. That means this it is whether it is if it is greater than or equal to 0, then how to what you have to subtract a surplus variable so that it will become an equation. So equations you should have the equations finally. Okay, then only the two-phase simplex method is applicable. Okay, if it is not, you proceed with actually you will you in initially you will proceed the entire problem you will approach it by it as a simplex method solving problem. Okay, so that you will get this system of equations other than inequality expressions. Okay, so yes, this is our problem, and if you proceed with this problem with simplex method, then you will have the non you will have the you will not have basic one solution known as basic feasible solution. Basic feasible solution does not exist here. Does not exist here. So if basic feasible solution does not exist, then we will go for the our two-phase simplex method. Okay, so okay. So here we have xi greater than or equal to 0. I varies from 1, 2, 3, 4, and 5. Okay, yes. Here the right side constants, right hand side constants of these system of linear equations have have non-negative. That means either positive or zero constants. Okay, and all are equal type. So we can introduce. So in the two-phase simplex method, what we are going to do is we will introduce variables known as artificial variables instead of introducing because we cannot introduce here a slack variable or a surplus variable because these are equations. Okay, so in this we will introduce some other variables known as artificial variables. Artificially created, you can say, artificial variables we will introduce. So how many artificial variables you have to introduce? That depends upon the number of constraints. We have two number of constraints here, so we will introduce two number of artificial variables. If m number of constraints are there, then we will introduce m number of artificial variables like this. y1 here, y1 and y2 artificial variables equal to. So m means m number of constraints means y1, y2, y3, y4, etc. up to ym artificial variables we will introduce. That means what we will do is 3x1 minus 3x2 plus 4x 3, okay, plus 2x 2x4 minus x5, okay, plus y1 equal to 0. So that will be our changed constraint. Our constraint got changed like this. And the second constraint will be having the change like this: x1 plus x2 plus x3 plus 3x4 plus x5. Then we will add the second artificial variable, that is plus y2 equal to 2. Okay, and y1, y2, yes. Okay, and then if you add, actually, normally if you add some artificial variables on the left hand side, you should add the same thing in on the right hand side also, right? That is what our math says. But in this case, it is we will next, in the next step, what we will do is we will define another variable, that is w. We will define w, and that is defined as w is equal to y1 plus y2. We will define, and we will try to minimize this variable w y1 plus y2 in phase 1 of our two-phase simplex method, so that our concept is same. That means a minimize, right? Our concept will be unaltered, will not be affected at all. Okay, so that means yes, this is our new variable, new function, that is w is equal to y1 plus y2. We will define it, right? And in standard form we are writing now. In standard form, we have to convert all these set of equations in standard form, in canonical form, okay, so that we can proceed with our tabular columns, or our iterations, right? So the next step is we will go for our standardizing each and every equations here. That means we have this. So our problem now got transformed like this. Minimize in phase 1. In phase 1, that is first phase of two-phase simplex method, our problem will look like this: minimize w is equal to y1 plus y2, okay, y1 plus y2, subject to, right, subject to the constraint yes, the constraints which is the same as our as given in the problem. These constraints given by this one system of equations. Okay, that means subject to constraints 1, right? Okay, and so in the standard form, what will be, we will write all our equations like this. That is, this constraints we have is Yes, we have 3x1 minus 3x2 plus 4x3 plus 2x4 minus x5 plus y1 equal to 0. And x1 plus x2 plus x3 plus 3x4 3x4 plus x5 plus x5 plus y2 equal to 2. Right. And this is 1. This is 1. And our objective function, that means our original objective function. Okay, objective function. That means objective function given by the exam. Objective function is in, again it is in standard form we have to write. So that will be like this: 2x1 right plus x3 x2 plus 2x3 minus x4 plus x5 plus x5 plus x5 okay, plus 0 y1 plus 0 y2 plus minus f equal to 0. 0. Yes. And we have our new objective function, newly defined objective function for phase 1. We have y1 plus y2 plus minus w equal to 0. Actually, this will be 0x1 plus 0x2 plus 0x3 plus 0x4 plus 0x5 plus y1 plus y2 plus minus w plus 0f equal to 0, like that. Okay, this will be like that. And yeah, that will be like this. And we have this equation as this is 3 and this is 2. This is 2. Okay, and in order to make in array in canonical form, this that means you can imagine this, the entire problem you can imagine as a matrix form. Like that means this an array format. That means this you can imagine as the first row. This is second row. You can imagine this is, and this is your third row. This is fourth row. You can imagine like that. Okay, then that becomes, and your first column. This is second column, third column, fourth column, fifth column, sixth column, and so on, like that. Then you can form a matrix with the coefficients here, right? So in that case, one more step you have to do in order to transform this equation number 3. You have to transform this in the form of x1, x2, x3 also. because here in equation 3 we have the coefficients of x1, x2, x3, x4, etc. as 0, right? So in canonical form, in standard form, you have to make it some coefficients you have to make it. So what we will do is we will add the equations in 1, we will add and subtract that equation from 3. Okay, that means from 3, that is like this, equation 3 minus sum of equations in 1. Then we will get the equation number 3 is transformed to so that means this procedure, this step is common, is common, or it is, you can blindly follow this step for any LPP, solving LPP using two-phase simplex method. Okay, that means equation 3 minus sum of equations in 1. That means in general you can say that the newly formed objective function in that has to be minimized in phase 1 minus the sum of all the constraints, equation. So that is the general form. Okay, general algorithm. The notes that I will provide to you. You need not to worry about it. So what 3 is now got changed into minus 4x1. Why? Because this y1 plus y2 minus, you will get minus y1 plus y2 you will get in the sum of the equations in 1, this term. So y1 plus y2 will cancel out. So and the negative will comes into picture. So minus 4x1 that you can that you will get if you do this operation. Okay, so minus 4x1 plus 2x2 minus 5x3 minus 5x4 plus 0x5 plus minus w equal to minus 2 you will get. So that is the canonical form. So we can have the canonical form like this. Canonical form like this is this minus 4x1 plus 2x2 minus 5x3 minus 5x4. This is our new objective function in phase 1 that you have to minimize it. And subject to the constraints, we have the constraints just like this. That means you have the new matrix form. For phase 1, we have the standard form like this. First of all, the constraints we will write, that is 3x1 minus 3x2 plus 4x3 plus 2x4 minus x5 plus y1 equal to 0. And the second constraint we have x1 plus x2, x1 plus x2 plus x3 plus 3x4 plus x5 plus 0y1 plus y2 equal to 2. And then we have our the main objective function, that is the original objective function which is given by the examiner. We have 2x1 plus 3x2 plus 2x3 minus x4 plus x5 plus minus f equal to 0. And we have the lastly we have the newly formed objective function, and that has to be used in phase 1 of two-phase simplex method, like this one writes here. That means here. Okay, so this is our canonical form. Now what we will do is, in the next step we will initiate our phase 1 of two-phase simplex method. And in phase 1 of two-phase simplex method, we will consider this phase 1. Phase 1. We will consider the basic variables equal to our artificial variables. Here we have the artificial variables, two artificial variables, y1 and y2. So we will execute the simplex method, the tabular method here. We will construct tables so that our artificial variables are eliminated completely. So in phase 1 we will solve for these artificial variables y1 and y2. Okay, so the procedure is same as the case of simplex method. So we have the basis for basic variables y1, then y2. Then we have the variables x1, x2, x3, x4, x5, then y1, y2, Then we have the solution bi of bi, and we have ratio column. Okay, so we will proceed like this. Okay, and we have the third row, for minus f and minus w. Okay, like this we have, here we have, okay, we have basis, and the artificial variables y1, then y2, then minus f, and minus w, minus w. And here we have x1, x2, x1, x2, then x3, x4, x5, y1, y2, then pi, solution, then ratio. Okay, so this is our table. Y1, so we will proceed with this simplex method in case 1. As y1 will be equal to, here x1, coefficient of x1 is 3. That means that corresponds to our first constraint. Okay, that means that the whole system, we are converting the whole system into the matrix form or in the tabular form. So here it will be 3 and minus 3. Okay, and 4, 2, minus 1. 4, 2, minus 1, 1, 0, 0, 1, 0, 0. And y2, 1, 1, 1, 1, then 2, 2, Then minus f, we have 2, 3, 2, minus 1, 1, then all zeros. Right. So then minus w for this w row we have minus 4, 2 minus 5. That is newly formed objective function. We have minus 5 and minus 5 here. Then here 0, 0, 0, 0, 0, and minus 2. Right. So in this case, what we will do is we will solve for we will eliminate the uh, the artificial variables one by one. Right. So it will be like this. That is, as, for in order to find out the entering variable, what you have to do, you have to observe or you have to check for the most negative value in the minus w row. That is, it is nothing but minus 5 here, minus 5 and again minus 5. Right. So this is a type. So what you have to do is you can choose uh, any variable as entering variable. You can either choose x3 as entering variable or x4 as the entering variable. You can choose any entering variable. Here I am selecting the x4 as entering variable. So this is our entering variable. And in order to find out what you have to find out next is you have to find out the leaving variable, right? So how you can find out the leaving variable? You can find out the leaving variable by filling this ratio column. In the ratio column, what you have to do is the 0 vi column corresponding elements divided by this entering variable column corresponding elements. So 0 by 2, that's equal to 0. That's equal to 0, you will get 0 here, we will get. And 2 by 3, you will get 2 by 3. Right, 2 by 3, like this, in this way. So minus f, you cannot, you are just maintaining that row. Okay, you need not to bother about minus f row in this case. Okay, 0, 2 by 3. So in this, if you have any negative values in the ratio column, you ignore it. You always consider the positive values. So then you have to take the most minimum of this positive values. So minimum value is nothing but 0. So this 0 will be the our 0 is leaving variable. Okay. Yes. So in the updated version of the table, what you have to do, what you have to write, you have to write this in place of this y1, you have to write x4 as the new variable x4. Okay, and then you should find this you have to make it 1, right? 1 you have to make it, and the elements you have to select that column as pivot column and this position as pivot position, so that in the pivot column the elements below and above the pivot position, or you have to make it 0, right? 0. Yes, like that you have to proceed. Then you will get the result of the updation of the table will be like this. Here in place of y1, so the y1 is leaving variable earlier, so y1 got relieved and x4 is entered and x4 sit here x4, and we have the pivot position here, pivot position here. So the pivot column is this, and that pivot column, the pivot position remains unity, and all other entries are made zero by row operations that we have already discussed. So after the all the row operations, the table looks like this. Okay, and in that case, in that updated table, or after that all that procedure, you have to find out the entering and leaving variables, right? So the for entering variables, we have to observe the minus w row. So, and the most negative number in that row you have to find out, and that element will be minus 11 by 2, and that if you look upward, then that corresponding to the x2 column will be x. This is x1, this is x2, and this is x3, x4. So that corresponds to the x2 column. So the entering variable will be x2, and the leaving variable, if you have to find out, then you have to fill the ratio. This is your ratio column, so you have to find out that. So how to find out, we have already discussed. Then you have to observe that column, and you have to consider all the positive non-negative numbers you have to consider, and you have to choose the minimum of that, and so that row corresponds to the leaving variable. So y2 is left from that at the end of this iteration. So at the end of this iteration, y2 leaves the table, and x2 enters the table. Okay, so in that way we have the phase 1. We have got the phase 1. So in the next iteration, what we will do, we will make this pivot position again 1, and we will proceed it, so that we will get this like this. We got this. Okay, here the yes y2 leaves, y2 left, and x2 entered, right? And this column, you have pivot position, you have made it 1, and the remaining entries are made 0 by suitable row operations, right? So what you will observe is if you observe the minus w row, if you observe, what we will get, non-negative, all entries are non-negative numbers, non-negative numbers, that is either 0 or positive numbers. So we got it. So that means our new objective function is got minimized, and the minimum value of this minus w is given by the uh, solution column, this solution column, that is b I star solution column. So minus w is equal to, that is minimum value of minus w is equal to 0. So w will be equal to 0. So the minimum value of this w we got as 0. So the first phase of two-phase method, simplex method, is finished. It is over. So you can drop happily. You can drop y1 and y2. You dropped. That means you have to eliminate. You successfully eliminated y1 and y2. That so that y1 plus y2 is equal to 0. Okay, and in the phase 2, in phase 2 of two-phase simplex method, we will proceed the tabular formulation with this. Here, is what we have entered into the phase 2 of two-phase simplex method. Yeah, by eliminating our artificial variables y1 and y2 got eliminated, and also our newly defined objective function w is got minimized to 0. So we will completely avoid this y1, y2, and w. Okay, w row we will neglect, or we will not consider anymore in phase 2, and we will proceed with our original objective function, that is this standard form of the original objective function. Okay, in that, let's get this out, is from phase 1 last table we will continue, right? So that means we have a minus f row as 98 by 22, 0, 118 by 22, 0, minus like that. And we will again carry out the simplex method in phase 2 also, by considering the basic variables are x4 and x2. We will continue that procedure. That means you have to find out the entering variable as well as the leaving variable. So here the entering variable will be minus 4 by 22, the maximum of minus 4 by 22 and minus 6 by 11. So the most negative value will be minus 4 by 22. So that column corresponds to this column of x5, and that x5 will be our new entering variable in the basic variables. So that will be our new entering variable, and you have to find out the leaving variable. Then if you have to find out that, you have to fill the ratio column. So this will be the ratio column, looks like, and 6 by 2 and 4 by 5. So the minimum of these two values is smaller value is this, and that, so that this x2 drops, x2 leaves from this table, and x2 is replaced by x5, the entering variable. Okay, so that, yes, this is our pivot element or pivot position, and that you have to make it as one unity, and all other entries in that column you have to make it 0 by suitable row operations. And then After doing all that, you will get this, like this you will get. That means yes, this you will get x4 x5, so x5 then x4 it got updated, then minus f is 21 by 5, 2 by 5, 5 0 0 minus 2 by 5. So this is this column, the entire row of this minus f got all the columns corresponding to the variables. We got all the values here non-negative, that is either 0 or positive. So we can stop our iteration here, right? And this column corresponds to our solution column. So what you will get is the solution as your solution will be yes, like this. That means all yes, here all the coefficients. That means you can have the real name of that coefficients as cost coefficients, right? So all the cost coefficients are having non-negative values. So phase 2 is also completed. So and the final solution will be like this. You can compare this column and this column. You can compare so that you will get x4 equal to 2 by 5, x5 equal to 4 by 5, and also we have to find out the solution for x1 x2 and x3. So these are not in our tabulation, so we can yes, without any doubt you can write x1 equal to x2 equal to x3 equal to 0. Yes, so and the minimum value of our original objective function is given by minus f is equal to minus 2 by 5. So but our original problem was to yes, was to minimize f, not minus f. So f is equal to f is equal to 2 by 5. That this is the minimum value of our original objective function. Okay, this is our problem solving. In two-phase simplex method. Okay, so now the next step or next what you have to do is I will give you the algorithm steps as a notebook, and you go through that algorithm steps so that you will get the general in general for For any kind of problem, you can have that general algorithm, so that can be easily understood on by comparing that with this video. Thank you.